Alrighty, let's get started. So welcome guys to the very first session of the very first crash course series that we're holding. So this extension 1 course, there's a lot to get through today, so we'll get into it straight away. So just a bit of housekeeping before we start. We will be pretty much speed running the whole way through because there is a lot to get through. The structure of it will be that you'll have 30 seconds to just think about the question, have a read of it, see if you know how to approach the question. Imagine that you're pretty much in an exam. See if you know how to do it. Just mentally map out the steps. After you've had that time to think, we're going to go through the question together. So you won't really be just doing the question on your own. You can do it as we do it as well, but you don't have to. And some of the questions will be skipped, but they will appear in the annotated version of these slides that will be emailed out. We'll just be skipping some because we just don't have enough time to go through all the questions. What we've tried to do is to get all the different types of exam style questions that may pop up, but obviously there's too much to go through. In terms of asking questions, ask questions during the mid-session break or at the end of the session, just because we have got so much to get through, we don't have enough time to stop. If you do have more questions, just feel free to email us. Oh, wait, can you guys hear me? So Rawaj. Is there anyone else who can't hear me? Or is it just Rawaj? All right, let me just move through the chat. I did a test with Rafid earlier today. It seemed to be working then. Okay. All right, Raj, just maybe try to. Actually, you can't even hear me, so let me just give me 1 second, guys. Okay. Yeah, so that brings me to pretty much the technical side of things. So keep your mics muted unless you pick up on a mistake, in which case just unmute yourself and let us know. If you do run into any technical issues like Rawaj seems to be having, just rejoin the session. Or if you really can't get in or there's some serious issue, you can contact admin and let them know. And at the end of the session, we'll be having a QR code that you'll need to scan. And through that QR code, we'll collect all the email addresses to which we'll email out the recording, the annotated slides, and the practice paper. It's so that the people who attended the session can actually get the resources. Okay, let's quickly talk through exam tips and tricks. So right now, there's 2 weeks until prelims, give or take. Maybe you have 3 weeks depending on your school. So if you're doing 7 subjects, this means that you have pretty much just 2 days of study per subject. So imagine if your extension 1 exam was in 2 days' time. How would you be studying if you had that mentality? So this isn't to like freak you out. It's that if you haven't started studying properly, this is just to push you along, but you really do not have much time until your prelim. So that's just the point I'm trying to make there. Now, in terms of where you should be with your study, all your notes for your content-based subjects should be pretty much finished by now. And in terms of maths, you should have wrapped up your understanding of all the concepts. Hopefully you finished almost everything at school. If you haven't, maybe try to get ahead and finish off the topics that will be assessed. You should be doing around 3 papers per week. I did say at least, maybe this is a bit much, but at least 2. There is only 2 weeks left, so it's pretty much crunch time right now. And when you do these papers, make sure you do them under exam conditions. So don't just like do them and then just like throw them away and not think about it. You'll need to check it first of all after you do it. But when you do it, make sure you can sit for those 2 hours and concentrate for those 2 hours, because it's one thing to do it in 10-minute blocks under no time constrictions, but it's another thing to have to do it under time conditions, and then make sure you check it afterwards to see if you've gotten all the questions right or where you went wrong. So this brings me to my next point. If you, after marking it, what you should do is you should subtract 10 to 15% to see how you perform in an actual exam setting. Because in your practice, you don't have that exam stress or the exam nerves, so you'll obviously do better in the comfort of your home. So whatever mark you get, subtract off 10 to 15%, and that'll give you an idea of what you get in an actual exam. So if you're aiming for, say, 70% in Extension 1, you should aim for around 80 to 85% in your practice papers. Now, obviously, to achieve all this, you'll need to create a strict study schedule. So if you don't have a strict study schedule, you probably won't be getting enough study time in to actually cover all the things that you need to. So I would recommend that you guys study 4 hours a day. That includes your other subjects as well. So if you're already having to do 3 papers per week, that's a lot of study time. So unless you have a strict study schedule that allows you to have, say, 4 hours of study per day, then it's going to be hard to get everything done. If you're only studying 1 hour a day, then it's definitely going to be hard to cover, the 7 subjects that you might have to study for. Okay, the last 2 things, if you don't already know, so Desmos is a great graphing calculator. So if you are not sure about how the graphing transformations work, or how sine graphs look, or how various different graphs look, this is a great tool to play with, and it's something that will really help you to understand graphing. The last thing is this website, and there's others as well, they have past papers. So if your school hasn't provided you with past papers, go onto this website here and you'll be able to find a bunch of past papers that you can try. The syllabus has changed. So I think 2019 and 2020 papers are the ones that you want to do. I'm not sure if 2018 was the new syllabus, but you can still try the old papers, but there just might be topics in there that won't be assessed. For example, circle geometry. Okay, next we have the topic order. So I will be doing the first 4, and Swadhin will jump on and take you guys for the second half of the topics. All right, so let's jump straight in. So we've got the first thing that we're going to do is inequalities. Now, the 2 main types of inequality questions that you would be faced with are the algebraic fractional and absolute value questions. We'll attempt both of them today. So here's the first question. Just take 30 seconds to have a look and think about how you might solve this. Think about if you already know how to solve it or not. Okay. So the first thing I would do here is I would move the 2 across to the right-hand side. So I have something like this. And then we know for these fraction questions, for inequalities, we need to multiply both sides by the square of the denominator. So let me just do that. Okay, and this will cancel with this square, leaving me with 4x minus 5 into 2x minus 3. And then I just have the stuff that I had on the right-hand side. What I'll now do is I'll bring everything to one side. So I won't expand everything because that's just kind of a longer way to do things. So I'll bring the right-hand side stuff to the left-hand side. And that will give me this. And then what I'll do is I'll factorize out 4x minus 5. Okay, 4x minus 5. That'll leave me with 2 times 4x minus 5 here, which would be 8x minus 10. And from this bracket here, I'll be left with 2x minus 3. So that's less than 0. Okay, let's come up here. So if we simplify the stuff in the brackets, we get 10x minus 13. Okay, and now I have a quadratic term here, fully factorized. So what I'll do is I'll just roughly plot this to figure out which values I need to take. So those are my roots. Then I draw my polynomial, and I want the part of the parabola that's underneath the x-axis because we're looking for the inequality where it's less than 0. So the values where the parabola is underneath the x-axis is between 5 and 4 and 13 on 10. All right, and that's the answer to this first question. All right, just give you guys a second to look at that. All right, let's move to this question. So these questions are probably the hardest that you'll be faced with in an exam. It's pretty unlikely that you'll get something like this. This is much more likely. If you have a look at past papers, it's almost always one of these questions. But you want to cover all your bases and make sure you know how to do every single question type. Okay, so with these inequalities, we know that with inequalities in general, we can have either the positive from the inequality. So let's say that we had some sort of function inside. We could either have the positive stuff, positive version of what's on the inside of the absolute values, or we can take the negative. And pretty much this is how an absolute value function works. It's actually a piecewise function, where we won't get into that much today. But what that means for this question is that we have 4 combinations. These both can be positive. This can be positive, this can be negative. This can be negative, this positive, or both of them negative. And what we need to do is just pretty much look at all the cases. So we'll look at both cases where they're positive. So this would be x minus 4, then x plus 2 is greater than 7. So pretty much just as we have it. If we solve this, this will give us 2x is greater than 9. And so x is greater than 9 on 2. Okay, so that's one of the potential solutions. Next one we'll look at is positive negative. So where this is positive and this is negative. So for the first one, we have x minus 4. If this one is negative, we pretty much just multiply it by minus 1. And this is greater than 7. And if we try to simplify this down, we get negative 6 is greater than 7. So first of all, this isn't right, but also it doesn't make any sense. So this pair doesn't work. Let's have a look at negative positive, where this is negative and this one is positive. This one also shouldn't work. So let's just have a look. So I'll multiply the first one by negative, keep the second one as it is. If this one comes out as 6 is greater than 7, that also doesn't make any sense. Okay, so we won't consider that particular solution. And then we'll look at the case where both are negative. Okay, so we have negative x plus 4, and then negative x, negative 2. It's greater than 7. This comes out as negative 2x is greater than 5, and x will be less than negative 5 on 2. Okay, so then these are the only 2 solutions that make any sense. So what we now need to do is we need to actually check these solutions. So this is saying, okay, x needs to be greater than 4.5. So what we can do is we can take a value greater than 4.5. So let's say 5, and we can plug it into 5 to see if, in fact, plugging in 5 gives us a result that's greater than 7. Okay, so let's quickly test that. So test x is equal to 5. We have 5 minus 4 plus 5 plus 2. This is 1 plus 7, which is 8, and this is greater than 7. So we know that this solution works. Okay, we'll also test something less than or something smaller than this. So this is negative 2.5. So let's test x is equal to negative 3. If we test this, you'll see that it also comes out as 7 plus 1, which is 8, and this is greater than 7. So this one works as well. So we can conclude that x is greater than 9 on 2, and x is less than negative 5 on 2. Okay, I'll give you guys just a second to look at that. Okay, let's move to the next bit of content, which is the pigeonhole principle. So pretty much the pigeonhole principle says that if we have k containers, that could be like colors, that could be marks, that could be literal pigeonholes. And if we have n items that we are wanting to fit into those containers, then the number of items in one container needs to be at least n on k. So for example, if you had, in this case, we have 7 pigeons, okay? And we have 3 pigeonholes. So we've got 3 boxes. And if we were to fit all those pigeons into the pigeonholes, you would end up with 3 in one of the pigeonholes. So pretty much when it comes to this, your thought process would be, how can I most evenly spread out these pigeons across all 3 pigeonholes? So you would place one at a time into the pigeonholes, but you would end up with one leftover pigeon, which you would inevitably have to put into one of the pigeonholes. So in this case, if we use a formula, we would have 3 pigeonholes, so 3 on the bottom, and we have 7 pigeons that we're trying to fit in. So this comes out as 2 1/3, and we would pretty much just round that up. And once you round it, you get 3, which tells you that one of the containers needs to contain 3. So this is the basis of pigeonhole principle. Hopefully you guys are familiar with this. We'll have a look at this question and we'll try to apply it. So this is a more straightforward scenario, and we'll look at a slightly more complex one in the next question. So just have a think of this. See if you know the answer to this after reading it. Okay, so in this case, we have 3 pairs of socks, so that's 6 in total. And what we want to do is we want to pick the least number of socks that way we can get at least one matching pair. So that's our goal. So in this case, the number of containers that we have are the colors, so black, gray, and brown. So we have 3 containers, and we want to figure out the n value so that we have at least more than one of the same sock type, so greater than 1. So if we go to solve this, then we can see that n needs to be greater than 3. Yeah, so it can't be 3, but it needs to be one more than 3. So it needs to be 4 socks that we pick. Now this question is pretty intuitive. You could do this without using the formula. If you just think about it with these questions, think about it as the worst case scenario. Let's say that you're picking socks. The first one you pick is black, the second one you pick is brown, and the third one you pick is gray. So the worst case scenario is that you pick one of each color, and so far you haven't picked any of the same color. On the 4th sock, you'll have to pick one of the matching socks, like one of the colors that matches, because you've already picked out all the colors. So that's why it's 4 socks that you need at the minimum. Okay, here's the next question. Have a think about this as well. So this one comes from North Sydney Girls, the 2020 paper. These are from the trial papers. Have a read of this and see if you can work it out. I'll give you guys 30 seconds for this as well. Okay, so with this question, you can score from 0 to 25. So that's 26 containers. But they've told you that 4 of the students have already scored 4 marks. So we already know that 4 have scored 25. So what we'll now do is we'll just look at a mark range of 0 to 24. Okay, and originally we have 130 students, but 4 of them have already scored full marks. So that leaves us with 126 students. So that means the number of items that we have is 126, and the number of containers that we have, or the number of pretty much marks that you can get, is 25, because from 0 to 24, there's 25 numbers. Now, if we use the formula, so n on k, this will be 126 over 25. If you plug that into the calculator, that gives you 0.4. Yeah, sorry, not 0.4, 5.04. And if we round this up, this gives us 6. So that means that another way to also break this down before we think about what this means is as 5 times 25 plus 1. So what that means is that out of all the containers, what you can do is you can place one student at a time in each of these containers or marks from 0 to 24. each container by the end will have 5 students each. So each mark will be attained by 5 students. And you have 1 student left over. And that 1 student will need to sit in one of those mark categories. So that means all of them will have 5 people, 25 out of 25 has 4 people, and then one of the marks between 0 to 24 will have an extra person, so 6. And modal will just mean what's the most common mark. So that will be that category that has 6 students in it. So 6 is the smallest value for n for it to be a modal mark. And that's the scenario where everyone is most evenly dispersed. Obviously, in real life, you would have more people scoring a particular mark. But worst case scenario, the least modal mark will contain 6 students. Okay, so now let's move on to permutations. We're doing okay for time. So with perms, this is where the order matters. So the other thing that we'll talk about today is combinations. That's when you're just selecting things. But with permutations, the order in which you place things actually has an impact. So for example, you could be arranging students in a row. So for example, ABC is one particular permutation, BAC would be another. When we look at combinations, each of these groups are the same because they contain the same elements. But permutations cares about the actual order of those elements. Okay. So the common types of questions that you will have in your exam are arrangements in a row. So this is pretty common. It could be students in a row, it could be items, or on a shelf, for example, books on a shelf. We could also be looking at arrangements of digits. So you could be asked, like how many arrangements of these numbers can we have, or how many arrangements of these letters of this particular word can we have? That's another particular type of question that comes up. And arrangements in a circle, that's also super common exam question. Let's start by looking at arrangements in a row. Now, some of these we will need to skip. So this first one we will do together. So have a read of this. See if you know how to do it. Part A and B should be pretty easy, but part C is one that's tricky. So have a read of this if you know how to do it. Okay, let's have a look at the first one. So here we have 6 students and 2 teachers. So altogether we have 8 elements. Now, if the 2 teachers are together, they basically turn into 1 element. And so we end up with 7 elements in total if the 2 teachers are bundled together. So the way that we can arrange from 7 elements is 7 factorial. But then we need to multiply this by 2 factorial because the teachers can switch amongst themselves. So hopefully that's not too unfamiliar. Part B, the 2 teachers are not together. So for this case, what we'll do is we'll look at the unrestricted combinations, or sorry, arrangements, which is 8 factorial. And we will subtract off. So the answer to this, sorry, if you actually plug it into the calculator, was 10,080. And then if we subtract off 10,080 from this, we get 30,240. So pretty much what this is saying is, let's look at all the combination, all the arrangements, and then we'll subtract off the cases where the teachers are together. So that's what we're doing here. And that leaves us with the scenarios where the 2 teachers are not together. Okay. Part C, there are at least 3 students separating the teachers. So with 3 students separating the teachers, that would mean that you can have 3, 4, 5, or 6 students separating the teachers. That's one way that you could do it. Or you could do all cases minus 0, 1, 2, cases. Yeah. So this scenario here is easier to work out because you don't need to work out as many situations as working out when you have 3, 4, 5, or 6 people separating the teachers. All we can do is just work out when we have 0 students separating the teachers, 1 student and 2 students separating the teachers. And then we'll take that figure and then we'll subtract it from all the cases to figure out the scenario that at least 3 teachers are separating, sorry, at least 3 students are separating the teachers. So let's start with 0 cases. So the case where there's 0 students separating the teachers, that is just where the teachers are seated together. Yeah, we worked that in part A, so it's just 10,080. All right, next what we'll do is we'll work out the scenario where there's 1 student separating the teachers. So we've got 1, 2, 3, 4, 5, 6, 7, 8 people in total. If there's 1 student separating the teachers, let's say the teachers are in these positions, okay? What we can also do is we can shuffle the teachers down. So the teachers could be here, but they could also be seated here, or here, or here, or here, or here, yeah? So that is actually 6 positions that they could occupy. This one here, 1, 2, 3, 4, 5, 6 that they could occupy with 1 student in between. But the teachers can also switch. So that gives 12 scenarios in which the teachers are separated by 1 student. And what we would then need to do is fill these gaps with the remaining 6 students. And then we can do that in 6 factorial ways. Okay, next, we have 2 students separating the teachers. Okay, so we have the same scenario again. Okay, let's say we have 2 students this time. Wait, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and here, the teachers can occupy 1, 2, 3, 4, 5 positions, but then the teachers can also switch amongst themselves. So that's 10 in total. 5 times 2 is 10. And again, the remaining seats can be seated with students in 6 factorial ways. And the final one that we need to look at, well, actually, we don't even need to look at 3, sorry. We just need to look at 0, 1, and 2. So in total, we have 22 scenarios here times 6 factorial, plus the case where we have the teachers together, so no students separating them, so 10,080. And what we'll do is we'll subtract this from the unrestricted cases. And this figure here will give us the scenario where teachers separated by at least 3 students. If we plug this into the calculator, this gives us 14,400. Okay, I'll let you guys think about that for a second. This part is pretty time consuming, but it is something that they could ask in the exam. Obviously, in the exam setting, you would have to be able to work that fairly quickly. Okay, let's move to the next question. So I'll give you guys just a second to think about this as well. See if you can attempt this one or if you know how to. Okay, so this question is slightly different to the normal alternating questions. Usually with those questions, we have more of one type of category. So here we have both 5 swimmers and 5 runners. Usually in an exam, it would be 4 swimmers and 5 runners, or 5 swimmers and 4 runners. But we can still do this question in much the same way. So what we'll do is we'll seat the swimmers in these positions, and then we'll seat the runners in these positions. Now for the first swimmer, there's 5 options to pick from. For the second swimmer, there's 4, 3, 2, and then finally for the last swimmer, there's only 1 person to pick from because you've already placed everyone down. Now for the runners, for this first runner, there's 5 options that we can pick from. This one 4, this one 3, this one 2, and this one 1. And if we just multiply these all together, you'll be able to work out the number of permutations. So this is just 5 factorial times 5 factorial. But we're not done yet, because we could also have the arrangement so that the runners are seeded first. So we could have runner, swimmer, so pretty much the other way around. So we'll multiply this by 2 to account for those cases, and this comes out as 28,800 if we plug it in. Okay, I'll give you guys just a second to think about that. This one's pretty straightforward, so hopefully this one's okay. All right, let's move to the next question. So have a think about this one. So this is the arrangements in a bookshelf scenario that we were talking about earlier. Ooh. Sorry, that's my go through this one. So here we have 3 different types of books that we're all putting together, we're all grouping together. So that gives us 3 items that we're grouping together. And those can be arranged in 3 factorial ways. And now within the maths books, because they're all together, they can move amongst each other. So that's 5 factorial ways to arrange the maths books. There's 4 physics books, so they can arrange themselves in 4 factorial ways. And there's 2 different chemistry books, so they could arrange themselves in 2 factorial ways. So if this one is a bit confusing to you, maybe draw out a diagram and see how those things are moving around. But essentially we have the maths books, physics books, and chemistry books that we can move amongst themselves, move amongst each other, sorry, the subjects. And then within the subjects, the books themselves can move amongst each other. Okay, here's the next question. Actually, we're actually skipping this one. This one comes from Hornsby Girls. This one will be in the annotated slide, so have a look at that. Okay, the next section that we'll be looking at is arrangements of letters. So let's have a look at this example, very typical exam question. I'll give you guys just a moment to have a read of this and see if you can work it out, or if you have an approach to work it out. Okay, let's have a look at this question. So we have 4 consonants and 3 vowels in the word Tuesday, and we don't have any repeated letters. So we don't need to divide anything else. So first question asked us that how many arrangements are possible if 3 vowels are together. So if the 3 vowels are together, we'll count this as 1 unit. And along with the 4 consonants, we have 5 units. And that can be arranged in 5 factorial ways. But the consonants can move amongst themselves in 3 factorial ways. If we plug this into the calculator, this gives us 720. Okay. Part B, the first and last places are consonants. So there's 7 letters. So 1, 2, 3, 4, 5, 6, 7. So if the first letter is to be a consonant, we have 4 options to choose from for the first letter. If the last place is also to be consonant, we're left with 3 options to choose from. And in between, we've used 2 letters out of the 5. So for the second letter, we have 5 options. For the next, we have 3, and then 2, and then 1. So if we multiply this out, this is just the same as 5 factorial times 4 times 3. This comes out as 1,440. Okay, part C, the vowels and consonants occupy alternate positions. So this is like the question or like the scenario that I was explaining with the runner, swimmer arrangements question. Typically, one of them is bigger than the other by 1. The bigger one you would need to place first. So I won't draw this one out, but you need to place the consonants first, and we can arrange them in 4 factorial ways, and the vowels can be arranged in 3 factorial ways. And this is equal to 144. Okay, so I'll give you guys just a second to think about that. All right. This question will be skipping, but it's very similar to the one that we just did, but there are repetitions. And remember, when we have repetitions, you just need to divide out those repetitions. So for example, here we have 3 S's, so you need to divide by 3 factorial. We also have 3 T's, so whatever you will have to divide by 3 factorial as well. And we have 2 R's, so you need to divide by 2 factorial. The way that you should approach these questions is as if there weren't any repetitions. So that will be the numerator, and the denominator, you would just be dividing out those repetitions. It will be in the annotated slides. So if you don't know how to do it, you can always look at the work solutions. Okay, let's now look at the arrangements of digits. So we'll take a look at this first question. I'll give you guys, again, 30 seconds to see if you know how to do this question. Okay, so with this question, 6,000, we want a number that's bigger than 6,000. So we've been given 5 digits. So if we form any 5-digit number, obviously by default be bigger than 6,000. We can form 4-digit numbers, and not all of those numbers will be bigger than 6,000. So we have to think about the restrictions there. Any 3-digit, 2-digit, or 1-digit number will obviously be smaller than 6,000. So we ignore those cases. We'll start off with a 4-digit number. So for the first option, if we wanted the number to be bigger than 6,000, we needed to start with either 6, 8, or 9. Because if we start with 4, it would be in the 4,000. So obviously it won't be bigger than 6,000. So we have 3 options. I don't know why I changed that to 2. We have 3 options for the first digit, 6, 8, or 9. After we've used one of those digits, we're left with 4 options for the next, and then 3 for the next digit, and then 2 for the one after that. So this gives us 72 possible numbers. We'll look at 5 digits now, and basically every 5-digit number will be bigger than 6,000. So we have 5 options for the first digit, 4 for the next, and 3, then 2, and then 1. So this is just 5 factorial, which is 120. So in total, we have 192 options or arrangements that we can use. Okay, hopefully this one's okay as well. It's a pretty standard question. Okay, let's have a look at this one. So this one, we will also be skipping, but this one comes from North Sydney Girls. So pretty similar to the one that we just did. The solutions for this will again be in the annotated slides. Okay, so next we'll look at the next type of questions, and this is the one that really comes up in exams, arrangements in a circle. This first one will be skipping, but let's take a look at this second question here. So I'll give you guys again 30 seconds to think about this. We're doing pretty well for time. Let me just check how many more questions we have. Okay. We might need to speed up just a little bit. Okay, so part A is a pretty standard arrangements in a circle question. We've got 5 adults and 2 children, so 7 elements in total. For circle arrangements, we do 7 minus 1 factorial, number of items minus 1, which is 6 factorial. This gives us 720. Part B, if the 2 adults must sit together. Okay, 2 of the adults must sit together. So if we group 2 adults together, we're left with, instead of 7 elements, now 6 elements. So arrangements in a circle would be 6 minus 1. But because the adults can switch amongst themselves, we'll multiply this by 2. So this gives us 240. Part C, if neither of the children can be seated together. Okay, so if neither of the children can be seated together, what we'll do is we'll do all the unrestricted arrangements minus the 2 children being seated together. So that will just be 720. That's the number of unrestricted arrangements. That was in part A. Minus if the kids are together. So if the kids are together, we'll again have 6 elements. So we'll have 6 minus 1 factorial for the arrangements in a circle, and the kids can switch amongst themselves. So this gives us 480. Okay, so how do we think about this one? See if you have any questions, which you'll have to ask in the mid-break, in the mid-session break. So if you do have questions, just note them down. So that way you don't forget once we get to them. Okay, the next question, let's see. Okay, we'll also be skipping this one. Very similar to the one that we just looked at. All right, now let's have a look at combinations. All right, this question comes from Roos. We will be attempting this question. So I'll give you guys again 30 seconds to see if you can map out how to do this question if you know how to do it. Okay. We are running slightly behind schedule, but hopefully we can make up time. Over the next few slides. Okay, let's have a look at this one. So the probability that the community there's at least 1 man and at least 1 woman. So we can figure that probability out by doing 1 minus the probability that there are no men and the probability that there are no women. So you can't really have a scenario, well, at least in the bounds of this question, where there's neither men or women. So you would not have any people on this committee. So we'll do the scenario where there are no men, which is all women, and the scenario where there are no women, which is all men, and we'll subtract that from 1. Okay, so for no men, what that means is that for your 5-person committee, you'll be picking them all from the 6 men. Oh, sorry, that's for the no women. So let's just do that one first. So we would have 6C5. Okay, so this is no women. So we're picking just from the men. And the denominator of this probability will be as if we didn't have any restrictions. So we're just picking 5 people out of the 13. So 13C5. Okay, and if we're to pick no men, then we would pick, so let me just write down the unrestricted combinations first. If we're to pick no men, it would be a committee of all women. So we have 7 women and we need to pick 5 out of those 7. So we have 7C5. Okay, and just to recap, the denominator there is just the unrestricted combination. So as if we're picking from the 13, we're picking 5 from the 13 people. Okay, if we put this into the calculator, this should come out as 140 over 143. So it's pretty likely that you'll have at least 1 man and 1 woman. Okay, part B. So 3 particular women and 2 particular men are chosen to be on the committee, and the committee members are seated at random around a circular table. What is the probability that the 2 men are not seated next to each other? So for this one, the easiest way to work it out is 1 minus the probability that the men are seated together Okay, so that would be 1 minus. Now, since we're dealing with probability, the denominator will be 4 factorial. So this is the unrestricted number of ways of arranging 5 people around a circle. So 5 minus 1 is 4, 4 factorial. The numerator will be 2 factorial times 3 factorial. So the 3 factorial comes from the fact that if we group the men together, then we're left with 4 elements. And if we arrange 4 elements around a circle, that can be done in 4 minus 1, 3 factorial ways. And the men can switch amongst themselves. So we have 2 factorial there. If we plug this into the calculator, this comes out as half. Okay. So I'll pause there for a second. Hopefully this is okay. All right, this question we will be skipping. This one comes from Holston. This one's a pretty standard question as well. So have a go at that in your own time. This one's from Sydney Boys. Also pretty standard. So have a go at that in your spare time. Question 4 here is a really tough question. Comes from Roos. Very interesting. So have a go at that in your own time. So this one's a really interesting question. Unless you go to Roos, I don't think you'll be asked a question of this difficulty in your exam. So that brings us to the next section, binomial probability. Now this is one of those gray zones in the Extension 1 course. It used to be in the old syllabus, but it isn't directly in the new syllabus, but sometimes they still ask questions. So we'll have a look at this one question. It comes from Manly. Have a read of this question, see if you know how to do it. So you can see it's a 2020 paper. So it has been assessed in the new syllabus papers. So have a think about this one. I'll give you guys maybe 20 more seconds. Okay, let's go through this one. So probability that a bullseye is hit twice. So you would have seen that he scores a bullseye every 3 shots. So probability that he'll hit a bullseye is 1 on 3. Probability he won't is 2 on 3. So probability he'll hit the bullseye exactly twice. So his shooting 8 times, he's allowed to have 8 shots. And we want 2 of them to be a bullseye. So it could be any of those 2. So of the 8. So it could be the first and the second, could be the third and the last. There's 8C2 ways of getting those 2 shots. Now the probability that he gets 2 shots is 1 on 3 squared, okay? But if he gets 2, that means he needs to miss the other 6. So the probability of missing the other 6 is 2 on 3 to the power of 6, okay? And you can see that this fits in with the binomial expansion stuff that you may have learned. And also another thing is that if these topics aren't being assessed in your prelims, if you've already got notifications, then you can pretty much just like gloss over these. You don't really need to know them. But if it is, then definitely put your attention towards these. So if we put this into the calculator, it comes out as 1792 over 6561 for the first one. Okay. Part B, find the probability that the bullseye is hit at least twice. So for at least twice, we'll do 1 minus 0 bullseye and 1 bullseye. So this is very much the same as the question that we've just done. So it'll be 1 minus, if we want 0 bullseyes, then we're not going to be hitting any of the 8. We will miss all 8 of them, and we won't hit any of them. Yeah, so this is the probability we'll miss all of them, and it can only be done in one way, missing all of them. Okay, and 1 shot, it can be done, you can get 1 shot out of the 8 in 8C one way, so 8 ways. It could be on the first, second, third, fourth, blah, blah, all the way up to the 8th shot. So 8 ways of getting 1 bullseye. That means you'll need to miss 7 of them, and you'll need to hit 1 of them, okay? So this is the probability of getting at least 1. So at least twice, sorry. So if we plug this in the calculator, it will come out as this. Okay, hopefully this is making sense so far. If this is pretty sketchy for you and you know you'll be assessed, then have a look at the recording. Okay, part C, very quickly. So we want a 90% certainty that we'll get at least one bullseye. So the probability of getting at least one bullseye is a probability of 1 minus no bullseyes, yeah? And we don't know how many no bullseyes we need to get to achieve 90%. So what I'll do is I'll put to the power of n here. So if we're missing 2 in a row, that's 2 on 3 times 2 on 3. 3 in a row is times 2 on 3 again, or in other words, 2 to the power of 3 cubed. But here we're missing n number of shots, so it's to the power of n. We need to work out what n is. If I rearrange this, I'll take 1 to the other side, and then I'll divide both sides by -1. This will give me 2 on 3 to the power of n is less than 0.1. So I've flipped the sign because I've divided by something negative. Sorry, let me just bring this down here. And what I'll do here is I'll take the log of both sides. This would be just that. And now I'll divide both sides by the log of the natural log. So if you haven't seen this before, this is just a natural log. Pretty much the same as your regular log, but with base e. And if I divide both sides by ln 2 on 3, this is something negative, so I'll have to flip my sign again. If I plug this into the calculator, this comes out as 5.68. So we need at least 6 shots to make sure that we have a 90% chance of getting at least one bullseye. Okay, I'll let you have a look at that for a second. Okay, the very last thing in terms of columns, so we are running pretty behind. So again, this one will be skipping. This one comes from Manly 2019, but it will be in the annotated slides. Let's look at binomial proof. So this is, again, another gray area, but it is still assessed. So you do need to be cautious of this topic if you are being assessed on it. So pretty much all these proofs are based on the fact that 1 plus x to the power of n can be expanded out in this way. So let me just write this out, and then I'll talk us through it. So let me just skip to the last term. Okay, so this can be expanded in this way. Hopefully you've learned this if you are being assessed on this topic. But what we can do is we can simplify this down a bit. So all these ones are to the power of something, but 1 to the power of anything is just 1. So I can rewrite all of these with just the x terms. Let me include this squared term here. And also I've gotten rid of this x because x to the power of 0 is just 1. Okay, so pretty much we'll be working off this expansion for these proof questions. Hopefully you've seen that before. Okay, so for this very first one, I'll let you guys think about how you might be able to use this proof. Give me 1 second, let me just copy this across because I will need to use this. Think about how you could prove this particular question. Yeah, okay, so Shayan, you could be asked to prove this. It depends if you've covered this at school, if you've covered binomial expansions, and this is definitely within the realm of proofs that you could be asked to do, you'll see that it has been examined in some past papers. This was a big part of the old syllabus, so if you want practice questions, there's heaps of those. Okay, so for this one, it's pretty straightforward. All you need to do is you need to plug in x is equal to 1, yeah? If you plug in x is equal to 1, we get 1 plus 1, which is 2. And we have 2 to the power of n here. And on the right-hand side, if I plug in x for 1, all these x's will just pretty much disappear because 1 squared is just 1, 1 cubed is also 1, and then we'll just be left with the coefficients. So this is how you could prove this. This one's relatively straightforward. Okay, let me move to the next one. So this one's a long one, so I've just already written this one out. So we can just quickly talk through it. So pretty much in this question, what they're asking you to do is to figure out the coefficient of x to the power of 5. Now, for the left-hand side, x to the power of 5 term is just given by 11c5, but on the right-hand side, we need to basically expand all this and expand all of this. And when we do, there'll be multiple terms that multiply together to give x to the power of 5. For example, the x to the power of 3 term from here can multiply with the x to the power of 2 term from here to give you x to the power of 5. So those two terms being multiplied, the coefficients of those two particular terms would be this. You could also have the x to the power of 2 term here, x cubed term here that multiply to give x to the power of 5, which have these coefficients here. And then you can just pretty much look at all the combinations and all the coefficients. And by equating the coefficients, what we can do is just add all of these together. And these are all the coefficients of x to the power of 5. Because remember, when you expand it out, you would group the like terms together. So these terms here would give you the coefficient of x to the power of 5. All of this would be equal to 11c5 because these two things are actually the same. That's the foundations of this particular proof. So have a look at this in your spare time after the session. But we need to get a move on. So this question I was going to go through with us as well, but we are lagging behind. For this one, what you need to do is pretty much what we did for the first question. Before you plug in x is equal to 1, you need to differentiate both sides, okay? And that will allow you to bring these coefficients in front of your select terms. Okay. All right, let's actually, since we're kind of behind on schedule, let's skip question 5 and we'll jump straight to this one. Find the independent term of x. So hopefully these questions aren't too hard for you guys. I'll jump straight into this since we're running a bit behind. Pretty much what you need to do is you need to figure out which term will give you the independent term. So in order to do that, this is NCR, because I don't know which term I'm looking for. What I'll do is I'll just isolate the x terms. I don't need to include the coefficients for this particular part of the question. This will be to the power of n minus 1, just to the power of r. So if I just look at the powers, what I want the powers to be equal to is 0, yeah? So what we've done here is we've added the powers together using our index laws. And from here, r is 3. So NC3, if we look at that particular term, this should give us the independent term. So I've just plugged this back into the actual term. So I've included the coefficients. And then if I extract this out, if I put the numbers together, and then I put the x terms together, so we have x to the power minus 2 cubed, that will give us x to the power minus 6. These will cancel out, yeah? So we are left with just the coefficient, which is just this. And we can leave it at that, or we can evaluate it. It will come out as negative 672 if we plugged it in. Okay. So let's keep moving. The next thing that we need to look at is related rates of change. Hopefully we can get through this. So we just need to cover related rates of change and polynomials in 30 minutes. So we'll try to spend 15 minutes on each. And then have a 10-minute break in which you guys can ask some questions. So with related rates of change, these are the question styles that you can be asked. And this may seem like a difficult topic at first, but it's pretty standard. There's a framework that you can use, and the types of questions that you can be asked are pretty limited. So it shouldn't be too difficult. We have examples for pretty much all of these question types. Question 1 is a triangle type. We'll be skipping this during the session today. This one you may not be asked in the exam because it involves differentiating a trig function, which you haven't learned yet in year 11. But you can still give it a go. All right, let's try this question though. So this one comes from St. George Girls, 2019. This should be, okay, so this is kind of messed up. This should be, you could just that. not these weird symbols. So have a read of this question. This one's a pretty popular exam question. So the guys in my class, we've already done this question before, but it's popped up in different school papers. So there's a good chance you could be asked this in your own exam. So have a look at this. Just have a read of it. See if you know how to approach this question. Okay, let's have a look at this one. So part A, we just need to prove this particular formula. Let's look at this one actually. So to do that, we'll look at this triangle here. You might need some more time to think about what's actually happening in this scenario, but pretty much this ladder starts with this position and starts to slide down the wall, and then eventually you'll hit Tom. Okay, if we have a look at the dotted lines, this triangle that I just pointed out, this length here is x, they've already told you that. This length here is 1.8 minus h. So we have x squared plus 1.8 minus h whole squared. Okay, so we're using Pythagoras. If you haven't already worked that out, that'll be equal to 2 squared, which is 4. Yeah, so this is a Pythagoras question style. You could also be asked a question where a boat is being pulled along and rope is being basically pulled in and it's attached to a wharf, and you're asked to calculate how quickly the boat is coming in. That is another type of common question, and ladders are the other type of common question with Pythagoras. Okay, but from here, all we need to do is make h the subject. So what we'll do is I will take the x squared to the right hand side, then I'll take the square root of both sides, and then I will rearrange this to make just h the subject. Okay, and this is what I end up getting. Okay, now for part B, it's asking us, all right, Tom is standing on the ground 1.6 meters away, and blah blah. At what rate does the base of the ladder hit Tom? Okay, so this is where the actual rate stuff comes in. This is actually asking us what dx on dt is. Okay, that quantity we don't know. We've been told earlier that the ladder is sliding down the wall at 0.5 meters per minute. So what that means is that this h value is getting bigger at a rate of 0.5 meters per minute. So we have dh on dt being equal to 0.5. Also take note of the units. So we're using minutes for the time, and for the actual quantity that we have, we're using meters. Okay, this will be important when we assemble a final answer. Okay, we have this quantity, we want to work this quantity out, and we will need to find another quantity. But for now, let's actually put this all into working. So we want to figure out dx on dt. So write that down first. Then what you should write down is a quantity that you have, or that you were given. So in this case, dh on dt. Okay, so we'll write down dh on dt. And then we need to come up with a quantity such that when we multiply it with dh on dt, we end up with dx on dt. So the quantity that I'll need is dh on the bottom, dx on the top. Yeah, you can see that the dh's will cancel, leaving me with dx on dt. Okay, this quantity I already have, but this quantity I can find. In this equation here, I have a relationship between h and x. Okay, so what we'll do is we'll differentiate dh on dx. If we differentiate this term, it's just 0. To differentiate this term, we actually have a shortcut. So whenever we have square roots, the derivative of that will be 2 times the square root itself on the bottom. So 2 times exactly the square root. I'm also keeping this negative here. The top of the fraction will be the derivative of the inside. In this case, the derivative of the inside is minus 2x. This will always be the case for square root derivatives. I can simplify this into x over 4 minus x squared. Okay. The question, however, needs me to write in dx on dh, which is just a reciprocal of this. So let me assemble this all together. And when I go to assemble it, I'll make that adjustment. So dh on dt, I was told was 0.5. So we'll plug that in. Times 4 minus x squared over x. Okay, so now I've got my rate function sorted. I need to work out, the question asks me, what rate will the ladder hit Tom? So Tom is standing 1.6 meters away from the wall. So x will need to be 1.6 by the time it hits Tom. So this question is kind of put in an extra layer for students to work out. Normally they just told you at which point they want the rate. But here we want it when x is equal to 1.6. Okay, when x is equal to 1.6, dx on dt will just be equal to 0.5 times the square root of 4 minus 1.6 squared. So we're just plugging in 1.6 for x and 1.6 on the bottom. Now, if we put this into the calculator, it will come out as 0.375, and we need to include our units. So here, we were told that it's in meters per minute. Okay, so we'll put in meters per minute. Okay. All right, so have a look at that. See if there's anything that you might want to ask during the session break. This is, I would say, a pretty typical question. It is a medium style or medium level difficulty question. So you could be asked this if you go to a selected school. The snowball questions are usually the easiest. But let's move to the next question. So this one, unfortunately, we might not have enough time to go through. We may have to come back to this. If we have enough time, we'll go through it. Actually, let's see. Actually, we should have enough time. Let's go through this one. So I'll give you guys just 30 seconds to think about this. This particular question type is pretty much as hard as you'll get. So this particular question from St. George Girls 2016 is pretty much as hard as these rates questions will be. So have a think about this. We'll see if we can finish this by 5:45, and then we'll move on to polynomials, which is the last topic for my half. So have a read of this. Okay, let's start to go through this. So this is a cone style question. Cone style questions usually use similarity. So we'll see how that will play in later. So water is pumped into a vessel constant rate of 24. So this should be cubed actually per second. So this is actually our dV on dt. We've been told that it's 24. The depth of the water is h at any time t. What is the increase in the area of the surface? So they want us to figure out ds on dt. Okay, when the depth is 16. So when h is equal to 16. All right. So let's try to assemble this and see what things we have and what things we need to figure out. So we have been told what dV on dt is. This is 24, so I'll write that in. And they want us to work out what ds on dt is, right, when h is equal to 16. Okay, so this is pretty much all we have to go off with the information directly from the question. But we do have some other bits of information. So we know that the surface area of this can be given by pi r squared, okay? So we don't have the radius here officially, but we'll just call the radius r, and we can figure out a relationship between this radius and h in just a little bit by using similarity. So we'll see how that plays in. We also have the volume of a cone. So this is a cone, and we know that the volume of a cone is given by 1/3 pi r squared h. Okay, but the thing is, we've just kind of worked out r, and it's not an actual variable, so we'll have to come up with a relationship between r and h, like I mentioned. But before we do that, let's see what quantities we actually need to work out. So ds on dt we need. It's the thing that we need to figure out. We have dv on dt, but that means we need to come up with a relationship between ds on dv. Now you can see that I don't have a relationship between s and v directly, okay? So usually I have a relationship between these two variables directly, and I can just differentiate it. But in this case, I don't. These two variables are connected via a third variable, which is r, or it could be h as well. They're pretty much the same thing. So by coming up with a relationship between s and r, and then v and r, we can connect these two variables. So let's see what we can come up with. So we need to come up with ds on dv, okay? And this is a very special type of rates question where we need to come up with an intermediary related rate in order to actually figure out the main related rate, which is what we just saw here. All right, so before I proceed, let me just use similarity to come up with a relationship, because that might help us before I actually proceed with the question. With these cone questions, you have two similar triangles. So if you have a look at this, we have a smaller cone here, and then we have the large cone here. In the smaller cone, we have a small triangle that's formed by the height, the radius, and the slant height. And it's the same thing for the bigger one. So if we use similarity, we have r on h is equal to, so I'm doing this side on this side. For the equivalent triangle in the bigger one, it will be 30 over 30. Okay, so I'm just using similar triangles here. You should provide a reason, but we'll skip that. It's in the slides though. And from here, I can figure out that r is equal to h. So this is just by using similarity. All right. And we'll see how this comes into play in a little bit. Now, let's think about this a little bit more. We want ds on dv. Now, we have ds. We can easily figure out ds on dr by differentiating this, yeah? ds on dr. So if we have ds on dr, what we can do is we can figure out dr on dv. If we can figure out dr on dv, these will multiply to give you ds on dv, okay? So ds on dr we can pretty easily figure out just by differentiating the first formula that we have. And by the way, even though we came up with this random variable r, it's actually just equal to h, okay? So we haven't come up with just something out of the blue. It's actually something within the question. Okay, now for dv on dr, I can just differentiate this and then take the reciprocal to figure out dr on dv. But the thing is, I can't differentiate this just as it is. If I differentiate this as dv on dr, I'll actually find what's called a partial derivative, because h and r are actually related. So I can't just take the derivative of one of the variables and leave the other. So what I'll need to do is I'll need to use information that h is equal to r and plug that in for h, so r squared times r, that gives me r cubed. So if I find dv on dr, this will give me pi r squared, yeah, for my quantity dv on dr. Now what I'll do is I'll plug that in. ds on dv is equal to 2 pi r times 1 over pi r squared. This will just come out as 2 over r. Okay, and I can go ahead and plug this now into my original related rate. So I've figured out what ds on dv is. I'll plug this into ds on dt. So I know that dv on dt is 24. I've just worked out ds on dv to be 2 on R. So I'll multiply this by 2 on R, which gives me 48 on R. Now they want me to work out the rate when H is equal to 16, but my expression is all in terms of R. But I know that H is equal to R, so this is the same thing as asking when R is equal to 16. So ds on dt, which is equal to 48 on 16, and this comes out as 3. So we can conclude that S is increasing at 3 centimeters squared per second. So this is a wonderful question. So it's pretty one of a kind, very difficult, but covers pretty much all the bases. And this is pretty much as hard as it can possibly get with the related rate of change. In the resources, we will provide a full written explanation to this as well. So if this is confusing to you, you can have a read of those written explanations. Okay, let's move on to polynomials now. I know we're rushing, but we have to. So with polynomials, these are the 3 categories of questions that you can typically be asked. So relationship between roots and coefficients, pretty obvious. Factor theorem and remainder theorem, and roots of multiplicity. These are the commonly examined areas. Okay, in the slides, we've included this almost extensive, maybe too extensive, almost too extensive list of formulas. You don't need all of them, but you can be asked most of these here. There's none of these that are outside the scope of what you could be assessed on. And what I've done is I've also kind of simplified these down into things that you can easily find. So maybe you want to remember this, which is just the cubic factorization. But then what I've also done is just manipulated this to get it to what you will need for the exam. So this is just fully in terms of now sums and products. Okay, these ones are for quadratics. These ones are for, or this one here is for a cubic polynomial. There are more. You can look at alpha cubed plus beta cubed plus gamma cubed. That is a long formula and highly unlikely that you'll be asked that in an exam. Okay, let's have a look at this question. I'll give you guys 30 seconds to think about how you would approach this question. Hopefully we can get through almost all these questions in the 15 minutes that we have left. So have a think about how you would approach this question. Okay, let me now go through this. So the first thing that you should have thought to do should have been to make it all into one fraction. So if we do that, the common denominator will be just what I wrote down. And the top components will be this. So this is just pretty much what each of these fractions will be missing from the common denominator. That's what we'll have to multiply top and bottom by. Okay, now the bottom is already something that we can work out pretty directly. It's just alpha, beta, gamma whole squared. Okay, but the top needs some work. So let's treat this as our a squared, this as our b squared, and this as our c squared term. Okay, now if we jump to the formula, this is actually this scenario here. So what that scenario tells us is that we need a plus b plus c whole squared. Okay, that's the first element there. And then we have minus 2 times AB, AC, and then BC. So we have minus 2, and we'll have a bunch of stuff in here, but that stuff will need to be AB, AC, and BC. So from here, this is our a squared term. So our a term will just be the square root of that, beta, gamma. The b term will just be the square root of alpha squared gamma squared, which is just alpha gamma. And then the c term will just be alpha beta. Okay, for here, for this one, I need alpha A times B. So that will be alpha beta gamma squared, and then need AC, which will be alpha beta squared gamma. And then finally, just expand this a little. And then the last term will be BC, which is A squared, alpha squared, gamma, and then beta. Okay. So I'm almost there. The stuff here is just sum of roots 2 at a time. So I have beta gamma plus alpha beta squared minus 2. Now, what I need to do from here is to factorize out the highest common factor, which is alpha beta gamma. And that will leave me with, well, let me do it in the right order. It will leave me with gamma plus beta plus alpha, which is the sum of roots. And the denominator is alpha beta gamma whole squared. Okay, now that I have that, let me just shuffle this over here. Okay, and I'll just plug in now my sum of roots, product of roots, and sum 2 at a time. So first, I have sum 2 at a time, which is going to be C on A. So that's minus 1. Then I have product of roots. So minus B on A, C on A. And then minus D on A will be the product of roots, which will be minus 3. And then I have sum of roots, which will be minus B on A, which is just positive 3. And divided by the product of roots again, which is, I think it was, yeah, minus 3. Okay. So in the annotations, you'll see that's positive 3, but it comes out as the same. But anyway, after you simplify this out, this is just 19 on 9 after you plug that into the calculator. Okay, this one's a pretty hard question. It comes from the Manley 2015 paper, 3 marks. Could you be asked this in your exam? Yeah, definitely. So you should definitely know how to do this question. If you know how to do this, you'll be pretty set for relationship between roots and coefficients. Okay, let's skip this one since we're on a bit of a time crunch, and we'll have a go at question 3. It's very similar to question 2. I'll give you guys just 30 seconds to have a read of this, and then we'll go through this. This is also a very typical exam question. Okay, so let's not read of this. The polynomial blah blah has remainder 8 when divided by x plus 1, and x minus 3 is a factor. So what that means is we'll use both the remainder and factor theorems to set up 2 equations, which will then solve simultaneously to figure out what a and b is. So if we use the remainder theorem for x plus 1, we'll be plugging in -1. So we'll have -1 cubed plus a -1 squared plus b -1 minus 6. This should give us 8. So this is just a remainder theorem. When we plug in -1 here, we should get 8. If we tidy this up a little bit, this tidies up to a minus b minus 7 is equal to 8. And we can tidy a little further to a minus b is equal to 15. Now for the second bit, we have that x minus 3 is a factor. So we'll plug in 3 into the polynomial. You don't need to show this substitution in your exam, unless it's a show that question, of course. And this should be equal to 0, because that's what the factor theorem tells us. This will tidy up. Let me skip straight to the most tidied up version. This will tidy up to this equation after I simplify this all out. Now I've got 2 equations. The easiest way to solve these 2 equations is just to add them. So elimination. This way the b's will cancel, and I'll be left with 4a is equal to 8. And so a is equal to 2. If I plug this back into one of the 2 equations, I can figure out that b is minus 13. Okay. Okay, so that's that question. So I'll give you guys just a second to think about this. Very typical. So make sure at least you know how to do this type of question. All right, let's jump to the very last question. Oh, actually, we also have this one. All right, let me actually go through this question. This question is a very difficult one, the Sydney Girls one. Maybe I'll talk us through the work solutions for that because we are a little bit short on time. All right. So with this question, have a read of this. See if you know how to do it. Again, this is pretty typical. It used to be pretty rare in the old syllabus, but it's since become a more popular question for teachers to go to. So I'll give you guys just 10 more seconds to have a read of this. Okay, let's have a look at this. So when a polynomial is divided by x by minus 1, the remainder is 3x plus 1. So far, what we can do is we can express this polynomial in this format. So just think about if this is confusing to you, imagine that we're dividing 3 and 7, okay? This would give you 2 remainder 1, yeah? So this is the thing that we're dividing by, x squared minus 1. This is what would, like the original thing, the polynomial, and this is the remainder 1. You can write 7 as 3 times 2 plus 1, yeah? So the polynomial, we can write as the quotient, okay, which we almost never know what it is, and it doesn't matter in these polynomial questions. Sorry, I messed that up. So the quotient was actually, the thing that we're divided by, is 3 in this case. So this is actually x squared minus 1. And the quotient, is 2, yeah? And the quotient we almost never know, like I said, but it doesn't matter. And then we have the remainder on the end. So if this looks confusing, it's actually something that's very intuitive. Now the question is asking, what is the remainder when we divide by x plus 1? So we just use the remainder theorem. We'll plug in minus 1 into this, and you'll see why it doesn't matter if we don't know what the quotient is. So if we plug in minus 1 squared is 1, minus 1, and then we have 3 minus 1 plus 1. Now this part is just 0, so we'll cancel out with this. So it doesn't even matter what the quotient was. We're left with minus 3 plus 1, which is minus 2. Okay, and that's that question. So I'll let you have a think about it. It's also really important that you guys know how to do this particular style of question. Okay, so what I'll do now is I'll jump to the very last question, the annotated version. So this is a very hard question, yeah? Very hard in the sense that it's very long, and you may be tricked out by missing an equation. You can see there's 4 equations that you need to come up with, and then you need to solve them simultaneously. So let me just quickly talk through how you can come up with the equations. We've just got 2.5 minutes left. Let's have a read of this. So we're given this cubic function. We've got a double zero at x is equal to 1. We've got a minimum value at minus 4 when x is equal to minus 1. So embedded in here is already 4 pieces of information. So let's go through this. If we've got a double zero at 1, so that means that 1 should be a solution to this. So if we plug in 1 into the original polynomial, x is equal to 1, we should get 0 as a result. But as you should know, for double roots, we can differentiate it, and a double root will also satisfy the first derivative. Okay, so once we plug in 1 into first derivative, this should also be equal to 0. So this is the second equation that we can set up. Okay, so that's the 2 equations that we can set up with this first piece of information. So let me actually just highlight that. So these first 2 equations, we can set up using that first piece of information. Now the second 2 equations, we can actually set up using this information that they've provided. So let's think about how that works. So we're told that a minimum value of -4 when x is -1. So first of all, minimum value is just a y value. And we're told that the y value is -4 when x is -1. So what that means is that if we plug in -1 into here, we should get -4. Okay, that's where one of the equations are coming from. Yeah. So if you plug in -1 into here, we should get -4. Yeah, that's just what this is saying. But we're also told that this is a minimum value. So what that means, and you may not have learned this yet, but in 2UNIT, the first derivative is actually connected to maximum and minimum values, okay? Maybe you have learned this, but when we have a minimum value, the x value that achieves that minimum value, when plugged into the first derivative, will give us 0, yeah? Or the way that you would solve it is you would find the first derivative and you would solve for x, yeah? But in this case, we already know what x is. So that means that if you plug in -1 into the first derivative, that should make the first derivative equal to 0. And so now we've got 4 equations. And the second difficult part of this question is to be able to solve these tactfully. So if you have a look at equation 2 and 3, they're pretty much the same. So if you subtract those, you'll be able to work out b is equal to 0. And once you work that out, you can just tactfully select pairs of equations to work out the other solutions. So I'll leave this to you guys to do in your time after the session. So that brings us actually to the end of my section. So the next section will be inverse functions. So now we'll take a 10-minute break. You guys can ask me any questions. So you can just unmute yourself or ask in the chat. So 6:10, we'll start again, and we'll be doing the second half of this session. So feel free to stand up and walk around, get a drink or snack. And I will transfer the meeting across to Suadin.
For the people that are still here, can you guys see my screen fine? Yes, all right, thank you. So we'll get started within like a minute. It's for you guys to settle back in. All right, we'll get back to it. Can you guys hear me fine? All right. So inverse functions are those kind of topics that are carried from term one. Now, they commonly test you on finding the domain and range for which an inverse function exists. And this is because for a function to have an inverse, it has to be a one-to-one function, meaning the original function, it has to pass the vertical line test and the horizontal line test. So it can't be a symmetric function of any sort. That's why normally when we're dealing with something like parabolas, we have to have a domain restricted to a certain value such that this parabola is a one-to-one function. The next up is actually finding the inverse of a function. So once you restricted the domain, if you need to, yeah, you find the inverse of a function by just substituting y as x and x and y as vice versa. And then comes a point of intersection of a function and its inverse. And this is usually done by solving the function as x, because to obtain an inverse function, you reflect the original by the line y is equal to x. And of course, the last part, sketching inverse trigonometric functions. So this is like cos inverse, sine inverse, tan inverse, and whatnot. We'll go through these graphs like within a few slides, just to like refreshen up. So a few tips when finding inverse functions. A useful thing to utilize is the vertex of a quadratic. And this is given by x is equal to minus b on 2a. And the y value as x at the y value as the function with x value as whatever this is. And this is useful for finding domain restrictions on a function, because remember, in a quadratic function, otherwise known as a parabola, it's symmetric about its axis of symmetry, or otherwise known as its vertex, right? So this function already isn't one-to-one, because although it passes the vertical line test, we definitely know it's a function for sure. It doesn't pass the horizontal line test. A horizontal line will touch this graph more than once. So it's not a one-to-one function, but it's a many-to-one function. And how you make this a one-to-one function is you choose a domain that's centered around this vertex or axis of symmetry, and you just ignore one side of it. So ignore the left-hand side or ignore the right-hand side of this x value. Next up is finding the intersection. Most students will just do, fx is equal to whatever f inverse x is. But this is going to be really hard, especially if your fx is something cool like whatever this is. Right? This is pretty hard to solve. So an easier way to do this is just solve fx with y is equal to x. Or alternatively, f inverse x with y is equal to x. And this is because this line is where the inverse functions intersect with the original function. Sorry, not this one. Just this one will be fine. And this is because, of course, inverse functions are obtained by reflecting the original graph by the line y is equal to x. All right, so here are some inverse trigonometric functions. So this is the function y is equal to sine inverse x. Notice that before we drew this inverse function, the sine graph, which actually looks, in real life looks like this, had its domain restricted because originally this sine function y is equal to sine x, just as it is a continuously oscillating function. It's not a one-to-one. It's continuously oscillating. It doesn't pass the horizontal line test. So before we drew y is equal to sine inverse x, we actually had to restrict the domain such that this sine graph is actually a function. Sorry, that's not sine, that's cos. Sine looks like this. Yeah. So that's really bad, but it's fine. So to restrict this graph, we actually took the domain from minus pi on 2 to pi on 2. You want to take the domain for which the function does not change concavity. Remember, when it changes concavity, I mean by going like this, right? From here to here, from here to here, the function changes concavity. It goes from decreasing to increasing. From here to here, function changes concavity again. Wherever it changes concavity, it's not a one-to-one function. This is why it's important to restrict the domain before drawing the inverse function. So anyways, for the inverse function, the domain is -1 to 1, and the range is minus pi on 2 to pi on 2. And something also useful to know here is that the domain and range of the inverse function is the range and domain of the original function. So for example, when we restricted the sine graph in the original function here, we did it from, so this is y is equal to sine x, minus pi on 2 to pi on 2. It's -1. Right? In the original function, y is equal to sine x, the domain was minus pi on 2 to pi on 2. And the range was -1 to 1. For the inverse function, obviously for the inverse function, to find the inverse function, you sub y as x. And this makes sense because you're reflecting along the line y is equal to x. The domain and range also switch. So the range of the original function is the domain of the inverse, and the domain of the original function is a range of the inverse. So that's y is equal to sine inverse x. Same process applies for y is equal to cos inverse x. This time the domain was also restricted at the point where it first changes concavity. Yep. So the domain is -1 to 1 for x and range 0 to pi. Now for tan inverse x, you know that's an asymptotic graph, right? The tan graph. It has asymptotes along minus pi on 2 to pi on 2. So in the inverse function, it has asymptotes along y is equal to pi on 2 and minus pi on 2. And because of this asymptotic behavior, its domain is x or real. It can take all real x values. And its range is minus pi on 2 to pi on 2, non-inclusive. I don't know why this equal sign is there, but it's actually non-inclusive. It never touches minus pi on 2 and pi on 2. All right. And now let's try a question here. So this question's from the Gira 2020 paper. And it's like one of those very generic like questions. You'll definitely be asked this if there's ever an inverse function question. So yeah, so part A asks, this question asks to consider this curve, x squared minus 4x plus 5. And we want to find the largest possible positive domain. So positive domain. This means that it contains only positive x values, for which fx has an inverse function f inverse x. Now, what we can use is, we have to start off with an x value, right? And this x value is given as the x value of the vertex of the parabola. Because remember, the vertex is where the parabola would change its rate. So as it's decreasing, then it's increasing again. So this vertex is going to be x is equal to minus b on 2a. That's going to be x is equal to minus 4 on 2, a is just 1. That's going to be 2. Now, because it asks for positive domain, we have to choose the right-hand side domain, which is x is greater than or equal to 2. If it was asking in general, we'd have 2 different domains that we can choose from. But of course, it's asking for the positive one, and this contains negative values. So cancel that one out. This is our answer. And that's that. Now, part B asks, find the point of intersection of this graph and y is equal to f inverse x. All right, now, the long method would be to find f inverse x using all that y is equal to x process and all that algebra, and then solve for x and y, which is going to be hard because you have 2 unknown variables. So we don't do that method. We actually do, the point of intersection is given by intersecting the line, intersecting the original graph, x squared minus 4x plus 5 to the line y is equal to x. So x squared minus 4x plus 5 is equal to x. That'll give you where the points where the graphs intersect. So just move the x over and then solve for x using the quadratic formula. 5. So that's going to give you 2 answers, 5 plus root 5 on 2 and 5 minus root 5 on 2. However, look at our domain. Our domain is x greater than or equal to 2. If you put these 2 on the calculator and evaluate it, we know that this is already going to be less than 2. It's going to be like 0 point something or 1 point something. So this is our answer here. X is equal to 5 plus root 5 on 2. And if you can just sub this value into the x value, it's gonna take the same x value because you're equating with y is equal to x. So the point of intersection is going to be 5 plus root 5 on 2, 5 plus root 5 on 2. So yeah, always look back at your original domain to find out which of these 2 answers is the most useful. Now part C asks, state the domain of f inverse x. So that's pretty easy, right? We note that we restricted our original function, its domain, as x greater than or equal to 2. Right, but for when x is equal to 2, for our original one, y is equal to 1. And because the parabola, we took the positive side, so it's always increasing. The side that we took is always increasing. We can safely say that the range, the restricted range, becomes y squared than or equal to 1. And now we remember that the domain of the inverse is the range of the original function. So just sub this y with an x here, and then you get your domain of the original function. Sorry, your inverse function. Now for part D, what is the equation of f inverse x? So here we have to use some algebra. So our original question, fx is equal to x squared minus 4x plus 5. Remember, to find f inverse x, let y is equal to f inverse x, and we swap the y and x values together, and we solve for y. In other words, we solve for f inverse x. So x is going to be equal to, remember we're subbing the y as x here, y squared minus 4y plus 5, right? Yeah. So we can't use the quadratic formula here because that will lead us with an answer in terms of x. Actually, no, we can, but you want to show more working out with like a more marked question. Another way to do this is going to be just completing the square. So that's minus 4 plus 5 is going to be 1. So move the positive one over. Y minus 2 whole squared. Now you want to solve for y minus 2, right? When you're square rooting something to solve y minus 2, it's going to give you plus minus an answer. So y minus 2 is going to be plus minus square root x minus 1. Move the 2 over. Y is equal to 2 plus minus square root x minus 1. Have a look at the domain of the inverse. I mean, look at the range of the inverse. The domain of the original is x squared than equal to 2. That means the range of the inverse is going to be y squared than equal to 2. This means that because we know that the square root is always positive, 2 minus the square root is always going to give us something that's going to be less than 2. So we're going to have to pick the one that fits our domain here. Fits our range for the inverse, which is going to be y squared than equal to 2. So that's going to be this answer, 2 plus root x minus 1. That's our inverse. You didn't have to include this last line of working out, but it's good practice. It shows that you found the inverse and not just random y variable. Now, part E, for the restricted domain, sketch the function and the inverse function on the same number plane. And we want to clearly label the graphs and its main features. Now, the main features that it talks about, this is also really important in curve sketching, is going to be x-intercepts, y-intercepts, and the intersections here. In curve sketching, I believe you have to show more like turning points if they ask, and maybe inflection points as well. But for these type of questions, we're only concerned with the x-intercepts, y-intercepts, and their intersection. So let's get this. Draw a number plane here. It doesn't have to be perfect, just any number plane would do. One important line to draw is going to be the line y is equal to x. And I like to label 2 different points just to know that my y is equal to x is good. So a fainted y is equal to x line, because this line is where the inverse and the original function will intersect, and where it's also reflected through. So our restricted domain, x is greater than or equal to 2, y is greater than or equal to 1. That's going to look something like this. That's going to be our original function. Fx is equal to x squared minus 4x plus 5. I'm going to change colors here. And our inverse function, remember x and y values switch. So it starts from x is equal to 1 and y is equal to 2. And it intersects this graph at this line. At this point, sorry. And this point is root 5. I forgot already. 5 plus root 5 on 2. It's going to look something like this. So it looks reflected along y is equal to x, and it also intersects this graph at y is equal to x. And that's going to be the inverse function. Yeah, 2 plus root x minus 1. So this type of question, very common. It sometimes can be hard with the algebra when you're finding the inverse function, but graphing them and plotting them shouldn't be too much of an issue. So does that make sense? All right, good. So this is from Karima 2020, and this question asks for you to sketch a trigonometric inverse. And it's not a usual trigonometric inverse. It's translated by 2 units to the right and dilated positively by a factor of a half, or increased its width by a factor of 2. So let's start off with part A, sketching this graph showing the intercepts on the axis and the equations of the asymptotes. Oh, there was already a page there. Okay. So remember our tan inverse graph looks something like this, right? It has pi on 2, minus pi on 2 as asymptotes, and obviously x is all real, starting off at 0. That's what the original tan inverse x looks like. But we first want to transform this to tan inverse x minus 2, and that's going to be translated 2 units to the right, and then transform this to tan inverse, then transform this to tan inverse half x minus 2. So it's going to be 2 units to the right, and the graph is also going to be widened by a factor of 2. That looks terrible. So let's sketch this now. Remember, nothing happened on the y value, all right? So the asymptotes stay the same. So we have a y-axis, x-axis, asymptotes will stay the same because nothing is being dilated in the y direction. And x-intercept would change because it's translated 2 units to the right. So instead of x at 0, x-intercept is going to be at 2. And y-intercept, we can find the y-intercept by subbing in x at 0. So y is going to be tan inverse half times minus 2, which is tan inverse minus 1. And the first answer you get on your calculator will be minus pi on 4. So yeah, not the best drawing, but you guys get it. Right, part B, the graph of the function is transformed by translation to the left by 1 unit, and then a horizontal dilation with a scale factor of 2. Now I want to find the equation of the transform graph. Right, so this is our original graph, all right? So when it's translated 1 unit to the left, the x in this graph becomes x plus 1. Not the x minus 2 becoming x plus 1, but just the x becoming x plus 1. So y is equal to 10. So let's first apply this translation because this is what first happens. Remember, for these type of questions, the order of translation, then dilation, or dilation, then translation is pretty important. It'll give you 2 different results of your graph. This one. And then horizontal dilation by scale factor of 2. Remember, when you have a scale factor of 2 in the horizontal dilation, your x values each actually decrease by a half. That's actually what makes your graph look wider. So the x value becomes half x. So y is equal to tan inverse half times half x minus 1. Common mistake, don't multiply the half by x minus 1 because that's saying that it only dilates the x minus 1 values by a half. That's not what it does. A scale factor of 2 means it dilates the x values only by a half. So we can just factor out the quarter out. That's going to be tan inverse a quarter x minus 2. And that's it. So does that make sense? This one was also like a generic kind of question. It's just that for part B, you want to look out for which is being applied first. So remember, we saw that the translation was applied first. That's why we did the translation first. Then we saw that the horizontal dilation was applied. And then after that, after we obtained the equation, after we obtained the equation for the translation, we made the horizontal dilation possible. Does that make sense? No. All right. Cheers, guys. So now moving on to trigonometric identities. These type of questions from memory from year 11, extension 1 maths, they don't get too hard at all. It's just a matter of like remembering your identities and your formulas. And that's the first thing I'm showing you guys right now. These are some common identities that you guys, I really recommend remembering. If not, I'd say compulsory remembering, because you won't have time to look back at your reference sheet for these type of questions 24/7. There's also a few others that I want that it's good to remember. It's going to be on your reference sheet anyway, but you should remember it. But these are cot theta is equal to 1 on tan theta, which is equal to cosine of theta on sine theta. Sec theta is equal to 1 on cos theta. Same with the cosec theta. The sum to 1 rule of cosine and sine. And these less common known rules, which come really helpful, especially if you're doing 4-unit maths. Because during integration, you're gonna have to be remembered this by head. So these ones don't have to remember it, I guess. They're in your reference sheet, but it's really, really good if you remember it. Products and sum differences. These are in your reference sheet. You can remember them if you want, but just a note that I went throughout high school without remembering this stuff. I just looked at the reference sheet. And same with this. This is also in your reference sheet. All right, this question is from SGG 2019. I don't know the full form of that school, but this is actually one of the harder questions. In saying that it requires a lot of algebra and a lot of thinking. So as usual, in any proof, we're required to prove that the LHS is equal to right-hand side. And the LHS is sine 3x on sine x minus cosine of 3x on cos x. And the RHS is just 2. From here, we start working onwards to complete our proof. So if anyone wants to answer, like through chat or through voice, what do you guys think our first move should be? We don't know any identities with sine 3x and cos 3x, but we know identities with sine 2x and cosine of 2x. So our first move would be to write 3x as 2x plus x. Now using our trigonometric way of expanding it. Yeah, that's right. Of expanding it out. Using the trigonometric angle sum formulas. We obtain this one. And remember, for cosine, it's going to be cos 2x, cos x, minus sine 2x, sine x. This over sine x, and this over cosine of x. Now, from here, it can get a little tricky. We know that if we combine it up, we're just going to get some messy blob that we're going to cancel out, but it eventually leads us back to this solution. What we now actually want to do is we can see that this fraction and this fraction have a common denominator with a sum or a minus in the numerator. We can actually split these fractions because we no longer have the 3x one, but we have the 2x, but we have the trigonometric identities in terms of 2x and x. So let's see what happens when we split these. This is plus cos 2x sine x. Notice these common terms that actually cancel out. Now, it's important before you split this fraction to put it in the brackets term, because in a fraction, the sign is always outside of the entire fraction. It's not part of it. minus sine 2x sine x on cosine of x. Notice common terms again, we actually cancel them out. Let's put a new page. Now, we can let's tidy this up a bit. But before we do that, now we can write sine 2x as 2 sine x cos x, and cos 2x. The cos 2x and cos 2x actually cancel out when we expand it. You guys will see. Let's do that first. Minus, so it's minus cos 2x plus sine 2x sine x and cos x. So the cos 2x actually cancels out here. But now we're left with these two. But we want an answer of 2, right? We know that this with the sine 2x formulas that we can use on both these fractions, sine 2x is equal to 2 times sine x cos x. So with this magic number 2 that we actually need to equal to, we can actually write sine 2x in this form. Sorry, plus, this is the left-hand side, plus 2 sine x cos x times sine x. Now notice these again, common terms cancel out, common terms cancelling out. That leaves us with 2 cosine squared theta plus 2 sine squared theta. Factor the 2 out, you have cosine of squared theta plus sine squared theta. This is an identity we already know. And this is equal to 1. So it's going to be 2 times 1, which is 2. That equals the right-hand side. Thus, proved. So, quite a long question, a lot of algebra involved. I don't know why this paper put it as 2 marks. In my opinion, in the prelims, these type of questions will be worth like an easy 3 marks. Maybe not 4 marks, but 3 marks. So it's you guys have to like really practice this type of algebra questions so you can see where you're at and where your answer needs to be. And I use that here because we need to be at 2, but my answer is sine 2x and sine 2x on both fractions. I picked up the identity that sine 2x is 2 sine x cos x. That 2 keeping me a hold on both sides of these fractions because it means that if 2 is on both sides of the fractions, I can factor it out. So yeah, does that make sense? Yeah. If you guys have any questions, just feel free to ask on chat, yeah? You can just direct message me as well. All right. Now a CNE Tech question. These type of questions are actually very, very easy 3 marks if you actually do it properly. But a lot of people, they tend to struggle because they tend to overthink and they try putting in the calculator and they get like a third, which can't be, which they don't know the exact value of. So first find the exact value of cosine inverse 2 on 3 plus tan inverse minus 3 on 4. All right. First of all, what type of function is tan inverse? Tan inverse, if we look at the graph, is actually a even function. So no, an odd function. Yeah, tan inverse is an odd function where f minus x is equal to minus fx. So tan inverse minus 3 on 4 is equal to minus tan inverse 3 on 4. All right, so let's rewrite that question. Sine cos inverse 2 on 3 minus tan inverse 3 on 4. And let's expand it. All right. I'll let you guys think. What do you think we should do from here? How can we obtain values of sine, cos inverse 2 and 3 and sine, tan inverse 3 and 4? Someone want to mention on the chat what we should do? Yes, draw triangles. Yep, that's right. Rawaj and Rafid. We want to draw triangles. So 2 triangles, because obviously they're going to be different. And here's why. One has an angle theta, one has an angle alpha. This angle theta is going to be cos inverse 2 on 3. So cos theta is going to be 2 on 3. Now what's cos theta? Cos theta is adjacent on hypotenuse, right? So that's the 2 is going to be the adjacent and 3 is going to be the hypotenuse. So 2, 3. And we can find the third side using Pythagoras theorem, which is going to be root 5. Right? So sine cos inverse 2 on 3 is going to be sine theta, which is root 5 on 3. So sine cos inverse 2 on 3, you don't need to write that again. Now alpha here is going to be tan inverse 3 on 4. So what's the hypotenuse? Hypotenuse is root 4 squared plus 3 squared, which is 5. So sine alpha is going to be sine tan inverse 3 on 4, which is going to be 3 on 5. Now we can solve this. That's going to be sine theta minus sine alpha. Root 5 on 3 minus 3 on 5. And yep, that's our answer. Any questions? That's good. Yeah. So easy 3 marks if you do it this way. This way is very simple and it's like a no-brainer once you know how to do it. So easy 3 marks. If not, then make sure you revise this question again, because it's really common, but it can throw a lot of people off. All right, this question is from 4th Street, and he asked us to use the T formula to solve this equation. You guys have to be familiar with the T formula here. The T formula for cos x is going to be 1 minus t squared on 1 plus t squared. And the same for sine x is going to be 2t on 1 plus t squared. And we want to solve this equation for 1. So let's do it. So t is equal to tan x on 2. And we obtain this from it. Now we want to solve cos x minus sine x is equal to 1. So 1 minus t squared over 1 plus t squared minus 2t over 1 plus t squared is equal to 1. Simplify the top. Multiply over. Just generic algebra. Now you want to collect like terms or just move everything to one side. That'll be easier because then you have a quadratic equation. 2t squared plus 2t is equal to 0, which you can just factor out. So the two solutions are t is equal to 0 and t is equal to minus 1. All right. Now, actually, no, I'll start a new page. That means that tan x on 2 is equal to 0 or tan x on 2 is equal to minus 1. It should be and, not or. So x is equal to 0 or 2 pi, or you can't equal to pi because tan pi on 2 is undefined. So just 0 and 2 pi for this one. And x on 2 is equal to tan inverse minus 1, which is tan inverse which is going to be minus 45 degrees, or sorry, minus pi and 4 radians. 3 pi and 4. This is out of the question because the domain is between 0 and 2 pi. So x is equal to 3 pi and 2. So these are your solutions. So how this works is, if you obtain the t formulas for this one, that's 1 mark. Getting up to this equation is going to be 1 mark. And actually solving the right answer is going to be another mark. That's how the marking scheme kind of works. All right, any questions with this one, guys? No worries. All right, this one's from James Roos, 2020. And this is honestly one of the very hard questions. And it's pretty long. Like, it's a lot of algebra required for it. That's fine. Let's try solve it. We want to show that all this is equal to this. Right? Let's evaluate the left-hand side first. So LHS sine 2 theta plus sine 4 theta minus sine 6 theta. Let's see where we're at and let's see where we want to get to. So we're at sine 2 theta, 4 theta, and 6 theta. And we want to get to sine 3 theta, 2 theta, and theta. We can already see here that 2 theta to theta, 4 theta to 2 theta, and 6 theta to 3 theta, we had to use the double angle property some way through. We can also see that since there's no plus and minus sign here involved, we've also cancelled out a lot of terms, grouped like terms together, and expanded stuff out. All right. Since 3 theta, 2 theta, and theta are involved, let's write these angles in terms of 3 theta, 2 theta, and theta. So the left-hand side is going to be all this, which is equal to sine, let's not use a red one, sine 3 theta minus theta plus sine 3 theta plus theta minus sine 6 theta. We leave the 6 theta as it is because we want to use a double angle identity for this one later on. Now we can expand this through sine 3 theta cos theta minus cos 3 theta sine theta plus the reason why we don't want to use it now is because we want to cancel out and group some like terms first. So these terms cancel out, plus and minus sign in the front, and these two terms group together. Now we can use the double angle property on this one. We know that sine 6 theta is just equal to sine 2 times 3 theta, which is going to be 2 sine 3 theta cosine 3 theta. Cos theta minus 2 sine 3 theta cosine 3 theta. We can factor out the 2 sine 3 theta out and put cosine of theta and minus cosine of 3 theta in the brackets. Now, if we look at our solution, there's no minus sign between. So we actually have to rewrite these again. And the way we rewrite it is, we know that 2 theta minus theta is theta, and 2 theta plus theta is 3 theta. So let's rewrite it in that way. Now we can expand because cosine of 2 theta, there's two different signs here. So we know that at least one of them will cancel out. So if you remember your cosine expansions, because there's a minus sign, we do a plus sign. It's always the opposite for cosine. Minus cosine of 2 theta because it's minus minus, there's going to be a plus sign here again. Oh, I did something here. It's meant to be cosine theta. And we're right, something does cancel out. And two of them actually group together. So that leaves us with 2 sine 3 theta, 2 sine 2 theta, sine theta. And we can just multiply the 2 and 2 here to obtain 4 sine 3 theta, sine 2 theta, sine theta, which is pretty much the answer that we need to get to. So that equals to RHS, and hence we proved it. So yeah, long process again, and a lot of algebra involved. So you need to be like comfortable with trying different type of methods for this type of question. Now it asks, solve this equation. Now, let me show you guys something. If we move this to the left-hand side, that becomes sine 2 theta plus sine 4 theta minus sine 6 theta is equal to 0. However, this is the same as this, right? So we can just equate to 4 sine 3 theta, sine 2 theta, sine theta is equal to 0. And that becomes easy to solve. So using part A, 4 sine 3 theta, and all that is equal to 0. So that leaves us with three different type of solution sets. First is sine 3 theta is equal to 0, sine 2 theta is equal to 0, or sine theta is equal to 0. And we want to solve for which domain? We want to solve for theta between 0 and pi radians. All right. So 3 theta would be equal to 0 pi. Okay, so for this one, it's easier if we actually manipulate the domain. So the domain for theta is 0 to pi. However, the domain for 3 theta is going to be 0 to 3 theta to 3 pi. We just multiplied everything by 3. So 3 theta would be equal to 0, pi, 2 pi, or 3 pi. So theta would be 0, pi on 3, 2 pi on 3, pi. So 2 theta is equal to 0. And theta would be equal to, so 2 theta would be equal to 0, pi, or 2 pi. Theta would be 0, pi on 2, or pi. The only unique solution that differentiates from this is the pi on 2. Sine theta is equal to 0. So theta is equal to 0, pi, or pi. And we see that these two solution sets are already included in the first one and the second one. So the unique solution for theta is 0, pi on 3, 2 pi on 3, pi on 2, and pi. And that's your 2 marks. So yeah, first question was pretty hard. I honestly think that part A should be at least like 3 or 4 marks. Part B will be definitely 2 marks. So any questions? That was a hard question, I reckon. Okay. All right, so next up is curve sketching. And it's probably the easier topics here. They can ask you some kind of weird curves, but the process is more or less much the same. So the examined areas are going to be reciprocal transformations. So something like 1 over fx, adding or multiplying ordinates, something to calculate fx plus gx using adding ordinates, or fx times gx by multiplying ordinates and whatnot. Absolute value transformations. So when it only outputs a positive value, or only x, or whatever x value is getting inputted as positive, or square root transformations. So only one question for this one because it covers everything you're going to be asked on. So we're giving this graph here, and he wants us to draw the reciprocal graph, the y-squared graph, the absolute value graph, and the absolute x graph. So let's take this step by step here. first, to do part A, what I like doing first is drawing like a dotted version of the original graph, because that's in that way it's going to be easier to apply transformations. Let me just rub this entire thing out. Yeah, that way it's going to be easier to apply your transformations. So where's the asymptote? Asymptote's at 3, and these are the intercepts. Oh, it's meant to be dotted. Now this is fx. We want to sketch y is equal to 1 over fx. All right. In a reciprocal, you want to treat each and every y coordinate as the reciprocal of whichever x coordinate it belongs to here. So in this graph, at -2 and 2, the y value is 0. However, 1 over 0 is defined as infinity. So at -2 and 2, the graph approaches infinity. In other words, there's going to be an asymptote at -2 and 2. It's never going to touch -2 and 2. Wherever there is a defined y value, there is an undefined y value. Defined as in like 0. So this is going to be an asymptote. At y is equal to -2, its new y-intercept will be y is equal to 1 over -2, so -0.5. And here, the graph is at a local minimum. The opposite is going to be true for the reciprocal graph. It's going to be at a local maximum, approaching infinity as it approaches -2 and 2. Because the original graph approaches 0 at -2 and 2, approaching the 0 axis here. The reciprocal graph must approach infinity. Now, the horizontal asymptote for the original graph was at 3. The horizontal asymptote, so asymptote horizontal for y graph is going to be 1 on 3, somewhere here. There's still going to be a horizontal asymptote here. All right. Now for the original graph, it's increasing along its asymptote. However, we have 2 different asymptotes for the reciprocal graph. So what it's going to do is, it's actually going to approach the asymptote still from underneath, but it's going to approach this asymptote as well. Same for the other side. And so this graph in blue is going to be our final graph. You didn't have to use the x and y intercepts here because you don't know what they are. You know what the y-intercept is because you can just do it from here, but you don't know what intercepts are. Something happened here. Yep, there you go. All right, any questions? Now let's move on to part B. So question 1, part B. Y squared is equal to fx, right? Y is going to be equal to plus minus square root of fx. So we know that we're going to have 2 different bunches here. So same thing, draw a dotted line of your original graph. And we want to draw y is equal to plus minus square root of fx. Let's start off with the plus square root of fx. Remember, when you're determining the square root of a graph, anything below y is equal to 0 gets ignored, simply because the square root of a negative number is undefined in the real numbers, in the set of real numbers. So you ignore whatever's below. And remember, for the square root graph, between the intercept and the graph, it increases more rapidly than the graph. then it starts increasing less rapidly than the original graph. Oh, one important thing I forgot to change was the asymptotes. The original graph has the asymptote y is equal to root 3. Sorry, y is equal to 3. Y is equal to plus minus x would have asymptotes y is equal to plus minus square root of 3. So root 3 and minus root 3. Yeah. It's going to be our new asymptotes here. It's going to be two asymptotes. Right? So first get your first branch. Then because it's plus minus fx, plus minus root fx, we have to sketch whatever is below as well. The same thing, but reflected below. Approaching the other asymptote. And that's your graph. Y squared is equal to fx. Does that make sense? Thank you. Okay, our next graph is going to be the absolute value graph. I'm probably not going to be bothered sketching the original graph dotted again. I'll just use this. So for the absolute value graph, whatever is below the y is equal to 0 line doesn't get ignored, but this time it gets reflected up. So the y-intercept becomes -2 or 2. So from -2, the y-intercept of absolute value of x becomes the absolute value of -2, which is 2. The x-intercept stay the same, and whatever is above the y is equal to 0 line stays the same as well. So the graph would look something like that. The asymptotes will stay the same if it's above the x-axis. If it's not, then it's going to have to change. But in this case, it is. So this is what the absolute value graph would look like. Just the bottom part gets reflected above the x-axis. And y is equal to absolute value of x. Now this one's interesting in this case. Let's look at this. So remember, y is absolute value of x. It means that for even negative values of x, it's going to output the positive case. So f absolute value of -2 would output f as 2. In this graph, we can already see that the graph is symmetrical, right? It's symmetrical here, and it's also symmetrical there. Whatever -3 -4 equals to, that equals to 3 or 4 and whatnot, right? So this graph already has the same y values for different signs of x values of the same value. So what do you think this transformation would do to the graph? Can anyone take a guess? Would the graph change? Yes or no? No one's responding. The graph actually, oh, someone responded. No, it won't reflect along the y-axis because this graph is already symmetrical about the y-axis. So yes, you're right in the general case. Yeah, exactly. It won't change. This graph won't change because it's already symmetrical about the positive y-axis. So the graph actually won't change in the absolute value case. So same graph. All right, any questions with just graph or curve sketching in general, guys? No? All right. Moving on. So mathematical induction, if you know how to do it properly, it's easy 3 or 4 marks. Very easy. And it's just to prove that a statement is true based on assumption, or mathematical framework. So it always involves 4 steps. To show that the statement is true for 1, usually k is equal to 1, or any initial value. To assume that the statement is true for n is equal to k. And using this assumption to prove that the statement is true for n is equal to k plus 1. That's where it gets its name, induction. It gets its name induction because it uses something to prove another thing. It uses an arbitrary case to prove a absolute case. And of course, the 4th step is to write down a conclusion. Now, normally it is okay to just write hence proved by mathematical induction. I know with the Hurlston kids, I think it's all right to do that, but I went to Macfields and my teacher just wanted the full form, like because it's true for n is equal to k, because it's true for n is equal to k plus 1, hence by mathematical induction, it's true for all n is equal to all this in the domain. Check with your teacher on which type of conclusion you need to use. But in general, for the HSC and prelims as well, maybe I don't know about prelims actually, but HSC definitely, you can use this proof. You can use this general proof. All right, so this question is from Sydney Boys 2010, and automatically we're already slapped with a hard mathematical induction question. And that's because in prelims, they'll rarely ever ask you easy mathematical induction questions, especially if you go to Macfields. So let's do this step by step. We want to prove that by induction that whatever's on the left-hand side is equal to whatever's on the right-hand side. So first step, check for n is equal to 1. So on the left-hand side, n as 1 will give 1 over x bracket x minus 1. And the right-hand side, it'll give 1 over x minus 1 minus 1 over x, which is going to be x minus 1, x minus, which gives you 1 over x minus 1. And that is equal to LHS. So therefore, true for n is equal to 1. Now, assume true for n is equal to k, where k is, okay, here it's supposed to be this. I'd say this is 3 marks. And n is a real number. Sorry, I'd say n is an integer. N is an integer. And x is a real number where x cannot equal to 0. Yeah. So assume true that for n is equal to k, where k is an integer, 1 over x, k, x minus 1 is equal to whatever's on the right-hand side. So just use whatever is given to you, but just sub in n as k. 1 over x minus 1 on x. All right. Now we want to prove true for n is equal to k plus 1, such that, so we're required to prove this. One is 1 over x k plus 1, x minus 1 is equal to 1 over x minus 1 minus 1 on x minus 1 on x squared minus 1 over x k minus 1 over x k plus 1. Always have this sneaky little 1 over x k here, because then it'll be easier to use your assumption. So this is what we need to prove. Now, this time we actually start from the right-hand side. Why? Because we know what all this is. This, we can use our assumption, where this is equal to 1 over xk brackets x minus 1 brackets x minus 1 minus whatever this is, 1 over x k plus 1. And that's using assumption. So let's expand the bottom and put this together. So xk let's leave the x minus 1 as it is. Xk, xk plus 1 times x minus 1. I'm going to put it into one fraction now. It's equal to xk plus 1 minus xk x minus 1. Let's put one more page. That's equal to xk plus 1 minus xk plus 1 plus 1 over. We can actually do something here. We can actually cancel out some of the common terms. Actually, no, we can't do that. Let's continue with the process. Plus xk, x k plus 1, x minus 1. These two cancel out, and this cancels out. That's going to give you with 1 over xk plus 1, x minus 1, which actually equals to the left-hand side of our required proof. This. So we use the assumption, and we proved for a 1 over x, for x is equal to, sorry, for n is equal to k plus 1. So therefore, true for n is equal to k plus 1. Hence, the statement is true by mathematical induction. So the mark distribution is like this. 1 mark coming from proving for n is equal to 1, another mark for using your assumption, and the final mark for your correct proof and conclusion. All right, any questions? All right. We got one more question to go. All right, so this one's from the St. George 2010 paper. And how many marks should I put this? I'd also say this is like around 3 marks. It's actually not a hard question unless you know your indices very well. So for mathematical induction proofs, you need to know all areas of the algebra pretty well. So you want to prove that this is divisible by 4 for all integers and is greater than or equal to 1. The smallest number we can prove for is for n is equal to 1. So we want to check that it's true for n is equal to 1. And we see that it actually is true for n is equal to 1. 4 times 1 is 4. Now we want to assume for a certain value k, for certain value n is equal to k, where k is greater than or equal to 1, that this is divisible by 4. Now, if we want to write divisible by 4, we want to write something as 4 times an arbitrary number. Let's say q, where q is an integer. So 5k minus 1 is 4q. All right, now we want to prove true for n is equal to k plus 1. So RTP, 5k plus 1 minus 1 is equal to 4w, where w is an integer. Q and w are just arbitrary numbers. They don't equal to anything. So anything that's absolute, they can be any integers. But more importantly, we want to use our assumption to prove this part. So LHS is equal to 5k plus 1 minus 1, which is equal to 5k times 5 minus 1. Now, using our assumption, right, 5k is going to be 4q plus 1. So that's going to be 4q plus 1 times 5 minus 1 using assumption. So continue. You can multiply the 5 over to have 20q plus 5 minus 1, which is 20q plus 4. What do you guys think we can do here now? How do you think I can prove that this is going to be divisible by 4? what do I need to factor or expand or simplify? What do I need to do? Someone say on the chat. Give you like a minute or two. Factor 4, yep, that's correct. I'm going to factor 4, and inside is going to be 5q plus 1. Now this 5q plus 1, because q is arbitrary, 5q plus 1 is also going to be an arbitrary integer. We can label this arbitrary integer as 4w, which equals to the right-hand side. So therefore, it's true for n is equal to k plus 1. And hence, by principle of mathematical induction, it's true for all n is greater than or equal to 1. So again, 1 mark for checking the initial case, another mark for using assumption, and the final mark for the correct proof and conclusion. All right. Is there any questions? You guys have any questions on how to, or like want me to explain this again? All right, no questions. Now that basically brings us to the end of the crash course. I want you guys, can you see this QR code that's on my front page? Yep. I want you guys to scan it. So when you scan it, you submit your email and you can get these resources emailed to you. So just take a photo of it. And we still have like 10 minutes remaining. So you can use this time to like take a photo or like get everything ready. Or you can just ask me questions on what we did today, on anything that we did today. Right. Do you guys have any questions from anything from inverse function onwards or during my part of the presentation? I'm happy to go through it again, like some parts. If you guys like don't have any questions and you're done scanning this code and everything, you guys are free to go. No worries. No worries.